Hi, welcome to 5.1, where we're going to start looking at the relationship between exponentials and logarithms. Mel's here to help out, but before we really get into that, we're going to talk about this thing, the letter E, and its application. Where it comes from is actually in finances. So there's these different types of interest. There's simple interest, where your interest is calculated once. This is kind of like there's this old idea of government bonds, like you gave them $50, and then 10 years later you can get $60 or something like that. Compound interest is what most interest works with. That as you gain interest, then it causes more interest to happen, whether that means you owe more money or your bank account grows faster and faster and faster. Um, Continuously compounded interest is something that's happening with stocks, where that interest is compounded infinitely number of times. So in the compound interest, there is something that's just happening like maybe once a month or once a week or once a year. That's what n is. If you're doing PERT, P e to the RT, you're continuously compounding that interest. What was noticed is that the more often banks were compounding the interest, they found that they were making more and more money. You can see it's the same interest rate, but if you divide up when you calculate that interest, it increases a certain amount, but it does sort of level off at a certain point. That is the number E. So you can see it actually as well if we do a cool example here. Here's that again, where we're actually calculating the number E. This is what E's value is. There's this cool thing called a limit. We'll do that in calculus. We're not doing it right now. So here's some examples of us actually calculating that interest. So it's just sort of a plug and chug type situation. You'll notice too, with that interest rate, I am doing it in terms of percentage rates. So I've got 0.06 instead of a 6. And then you want to say, okay, how many times a year is it happening? So for the second one. So we're calculating twice a year, so 2. With the compounded continuously, we make the most amount of money because we're calculating the interest the most number of times. She's leaving now, so you might need to rewatch some of that as I'm fighting with my cat. I'm not worried too much about that, so you don't need to necessarily write all of that down verbatim. What I do want you to write down is this, the graphs of exponential functions. So exponential functions have their initial value, that is this a, and then they have a base b, that is the thing that has our exponent. Now we don't want this thing to be 1, because if our base is 1, we just have a boring flat line. That's not an exponential function. There are 2 different categories. B could be between 0 and 1. It can't be negative, because then it's definitely not exponential. And it also could be bigger than 1. If it's between 0 and 1, we get this, which is exponential decay. If it is bigger than 1, we get exponential growth. The idea is that exponential decay runs to the x-axis, and exponential growth runs away from the x-axis. It could be going down, it could be going up, or it could be running to, or it could be running to, but from below. That's depending upon whether our initial value is either greater than 0 or less than 0. Horizontal asymptote is what it is going to approach but never cross. There's that idea of that limit again. So in our basic one, it is the x-axis. That is the line that it is approaching, but it is never quite reaching. You can see it approaching it on this side for an exponential growth, and it's approaching it on this side for an exponential decay. Major thing I want you to be able to do, and this is where we hit the real meat of today's lesson, is making sure that we can graph these exponential functions. So exponential functions, there's 2 points that we really care about. We care about that initial value, so that a value. In this first one, it is just 1. Bop. Because there's 1 in front of that 3 to the x. We also want to put in the first value. So what happens if we do it to the first power? Because that's the easiest one. And once we get that, we get enough to basically make this graph. So 3 to the first is 3. So 1, 2, 3. So using that, we can tell that it should be an exponential growth graph. So we go whoop. And as a horizontal asymptote right here, at 0. So this is meant to be like on that x-axis, but I can't do it perfectly. The domain of this function, you can probably spot this in your happy function book. Our domain is going to be all real numbers because we don't have any problems in terms of our domain. Our range is we can't go negative. We can't even touch 0. So it's going to go from 0 to positive infinity. Now, I want to make sure that you're cool with your transformations. You can spot this in your happy function book. If we get a +1 inside of that function, because it's inside of the exponent, that means it's going to be moving left and right. If it's plus, it's opposite of what we'd think. We would think that plus would be to the right because it's a positive direction. It gets backwards and weird on the inside. So what we want to do, and I'm going to cheat a little bit because I'm working on a digital device. You can just do this on paper, write the final result, is we want to take our regular graph. So there's our regular graph right there. And I want to take everything that's going on with it, and I want to move it to the left 1. Whoop. Because that is what that transformation is doing. It's taking everything about this graph and moving it to the left 1. Because this is left, oh, excuse me. Left 1. So we end up with this new graph. Is this all linked together? Because I hope you are. Yeah, this new graph where everything has been moved to the left 1. Let's check what that does to our domain and range. Our domain is still all real numbers. I don't see any problem with the x-axis, with the x values. Our range is all of the y values. And still, it's like, okay, well, I still can't get past 0 because that's where my horizontal asymptote is. So I can approach 0, but not quite get there. Mel likes that too. I guess she didn't want to come back. Now the other one, the +1 is on the outside. So we've got this +1 on the outside. So it's going to tell us we want to go up 1. If it's on the outside, it's going to move it up and down. But if it was minus Mel, then we're going to go down. But because it's plus, we got to go up. Okay? Okay. So I'm going to once again take this graph. She's going to bite me. Just watch. I'm going to take this graph, duplicate it, and I'm going to take all those points. Here's where they were before. And I'm going to take all of those points and my horizontal asymptote, and we're going to pull it up, whoop, 1. So everything gets moved up 1 spot. I would like to change the color of that. We'll make this one red. So since everything got moved up 1, our x values, we're still hitting everything. There's no problems there. So it's still all real numbers. You're so helpful right now. I really appreciate you being here. I don't. So it's all real numbers. And our range has changed. All of those y values have increased by 1. So we can't reach 0 now. We can't even reach 1. So our range is from 1 to infinity. Now, before we start talking about logarithms, I want to spend a few minutes talking about this big old graph. So this idea of a logarithm and an exponential is that they are inverses of each other. We're taking everything that's in this graph and we're swapping it around over into this one. This is a very big deal, so make sure you've got a nice big page that you can fill up a piece of paper with this thing, because it's very, very important. Mel's starting to bite me now. She might need to go. So exponentials have a horizontal asymptote, while a logarithm has a vertical asymptote. And the reason is that they are inverses of each other, and they are mirrored over that line, that pink line down the middle of y equals x. That's what every inverse is, because it's taking the x and y values and swapping them around. You can see that these tables match, but they're just reverses of each other. Have this in your brain. Have this like a nice big piece of paper that you can recite and recreate everything that's on this page somewhere in your notes. If you need to pause the video, go right ahead, but make sure that this is in a very special place in your notes. Let's make a couple logarithmic graphs. To make these logarithmic graphs, we care about two numbers, just like we did for an exponential. In an exponential, we cared about these two, 0, 1, and 1, 0. We're going to do the same thing for a logarithm. No biting, no biting, no biting. She doesn't like logarithms. I don't like them. So we want to do 1 and the base for every logarithm when we graph. We need 1 and the base. So we're going to do 1, and that 1 is always going to be 1, 0. All of these go through 1, 0 for a basic logarithm. We're going to talk about transformations in a second. And then we do our base, which is at 3. So 3, and then we convert that 3 and then 1. So it's always going to be our 2 points, always going to be 1, 0, and then our base, 1. Right there. And you can see that if you kind of like rotated it, and we'll flipped it, I'm sorry, not rotate, flipped it over the y equals line, then we get that same graph that we had before of our exponential. See that? See how they're mirrored from each other? Great. We're going to have a vertical asymptote now on our y-axis. And then our graph is going to kind of curve away. This will go kind of straight down, but it'll kind of curve away. This is not an exponential growth or an exponential decay. It's a logarithm. Our domain for this thing, since it's an inverse, it's going to be the range of our original function. So it's going to be from 0 to infinity. That is the range that we had on that earlier problem. See? 0 to infinity. Our range for this thing is going to be the domain of the original function, which was all real numbers. So we're going to have all real numbers here. Transformations are a little bit more obvious with this one. We can tell that this is on the inside. Since it's on the inside, we want to go left and right. It's subtraction, so I might think left, but it's actually going to go to the right. 2. This one where it's a minus 2, it's got to go down 2. So let's graph both of those. So can I grab all of this, please? Oh, I don't want the graph. So you lock. Up. Almost. All right. So I'm going to duplicate this. All right, so there's our regular graph. And what I want to do is I want to take everything and move it to the right 2 spots. So 1 spot, 2 spots. So there is our graph of this function. Did another one. Nope, I don't want to do that. I want to take everything that we have here and I need to move it down 2. So I'm going to go down 1 spot, 2 spots. Now keep in mind that, let's make that pink. This graph is still going higher up. I'm sorry, yeah, the graph is going higher up and our asymptote is still going up. Our domain for this one, now we can't necessarily use the domain and range of the original one because we don't have that for this one. But I can just look at this graph and figure it out too. So the domain, it seems I'm stuck at 2. I can't go past 2. I've got a vertical asymptote there, so I can't quite reach 2. And I can keep going to infinity. Our range, there's no problems going up and down, but it's all real numbers. Our domain for this other one, we can't get past 0. And our range, we can go all the way up, all the way down. So all real numbers. And that's it. That's it for today. Yeah, that's it. It's a little bit fast. I'm mostly interested in you knowing about this graph. This is the biggest deal of today. If you learned nothing today, it's making sure that you know that exponentials and logarithms are inverse functions of each other and that they are mirrored over the line y equals x. Very, very important stuff there. Okay? Thanks for watching. Have a good day.